Yes, sure. Yeah. No, just do it like you did it. Okay. Yeah. Okay. Yeah. Do I have those here? No. Can I see that problem? Okay, so on stresses and beams, number one, um, the beam looks like this. There's a pin joint over here and a roller in the middle. Um, each of these lengths is 0.7. There's a force at the end of 15,000 newtons. It gives the angle with the vertical, but you can think of that as an angle of 30. And the beam has a weight of 10,000 newtons. That's a heavy beam. It's made out of like neutron star. Some idiot made these problems. Circular cross section with a radius of 0.02 meters. And you have to calculate the internal loads and then calculate the stress tensors, except we can't do the whole stress tensor yet. We can only do the normal stresses, and the only normal stress is the X normal stress. Is there any way for me to, do you have the answers for the, can you just tell me what the answers are? So we're going to have two cuts. This will give me a chance to write. So these are piecewise functions. So you can think of the internal tension as having one value for X between 0 and 0.7, and another value for X between 0.7 and 1.4. And what are the tensions? They're both going to be the same, aren't they? 12,000. 900. 990.4 for both. Okay, and then the shear force. Well, I guess we don't even care about that. We don't know how to calculate the stresses yet for that. We don't care about the torque. There's no torque. And then what's the function for the bending moment? That's going to be two different ones. Okay. Okay. Okay, that's for X between 0 and 0.7. All right. Okay. 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 So let's just do this. I'll just do this for one of those two. Um, so on the first interval, on the interval um, x values between 0 and 0.7, the stress due to tension compression is sigma xx is equal to negative 12,990.4 divided by the cross-sectional area, which is pi times 0.02 squared. And what do you get for the answer? Okay, can someone do that? Okay. And now the bending moment. So this one, for every point in that first half of the beam, this is the normal stress due to tension compression. So that doesn't vary x, and it also doesn't vary with y. It doesn't, every value has the same stress due to tension compression. But that's all going to be different with the bending moment. Yeah. Okay, so for this one, the stress is equal to negative my over I. We have to calculate that I. Let's see. So, all right. So I is equal to pi r to the fourth over 4. 2 or 4? 4. So can someone calculate that with r equal to 0.02? We're dividing by this tiny thing, so let's put a lot of significant figures in there. 25664 times 10 to the negative 7. And that's meters to the fourth. And so the stress is, so we have this function. We have negative, we're taking the negative of my over I, so I'm just going to multiply the negative 1 through. So 3571.4 x squared plus 7500x times y divided by 1.25664 times 10 to the minus 7. And let's just divide this out into a polynomial. So 3571.4 divided by that denominator. Times 10 to the 10, and then times x squared times y, and then plus Okay, times 10 to the 10 xy. Okay, so this is our function for the x normal stress due to the bending moment. And what that says is that if you have and we're only looking on the first half. Okay, so here's our beam. And say that we want to know the stress of, some point over here. That point has this x value and this y value. Okay, and plug that x and y into this expression and it'll give you the stress. So x ranges from 0 to 0.7, y ranges from negative 0.1, no, the radius is 0.02, right? So negative 0.02 to positive 0.02. So if you choose a value outside of those ranges, then it doesn't have any physical meaning. But that's the idea. And then, so the total x normal stress is 2.842 times 10 to the 10 x squared y plus 5.9683 times 10 to the 10 xy minus 1.034 times 10 to the 7. Where is that going to be? Biggest value of that is going to be when, well, I don't know what that function looks like. It's going to have a y value all the way at the top, you can see. So with y equal to 0.02, and you could find maximums of that. By the way, finding the maximum of a function like that is a useful thing because usually you're trying to figure out whether this thing's going to break or not, and so you want to test the place where that stress is going to be biggest to see if there's going to be a fracture starting there. Yes? Yes. You know why? The neutral axis, exactly. Yep. So it is always the case that when y is equal to 0, you'll have no stress due to the bending moment. And that's because where you locate that y equals 0 is you put it on the neutral axis. But that doesn't mean the total x stress will be 0 there, as you can see here, because you still have x normal stress due to tension and compression. Okay. I have like 4 of Ellie's problem sets sitting in my office because she keeps like giving them to me for me to do this, and then I just put them in here and leave. She has to print it out again. It's hilarious. Yeah, exactly. It's a good idea. Okay, so back to the stress due to shear force. So what I said was the stress, it's going to be a shear stress, and it's going to be the XY element And the value is equal to negative V, that's the shear force, times Q divided by IB. B is the width of the cross section at the point in question. And so to use this formula, the only thing we need to know is this Q. Okay, so I have to tell you how to calculate that. And I don't, I guess it's the first moment of, I suppose it's the first moment of area. I don't know of people calling it the first moment of area. So I'm just going to call it Q. Okay, so let's say that we start with an arbitrary cross section. Okay, so let's say that's our cross section, and this is we're imagining like the beam extends back into the page. We can't trust if we had a cross section like this, we don't have any techniques that would accurately calculate the stress, but this mathematical thing Q still has a meaning for this. And let's say this is the neutral axis. That means that it goes through the centroid of the shape. And let's say we want to calculate Q at this line. So we want Q here. Okay. Then take the area that's above that line and locate its centroid. So this is the centroid of the whole cross section. This is the centroid of the area above that line. This shaded region has an area A. And then calculate the distance from the neutral axis to the centroid of the shaded area. I'm going to call that distance D. Then Q is equal to the area times that distance D. One really interesting mathematical fact, it makes you want to go through try to prove it. Cool factoid. Q, using the area above the line, the line of interest, always equals Q using the area below the line of interest. It's not the same area or the same distance, and they always equal each other for any shape. So, in other words, so if this is your cross section, and here's the neutral axis, and this is your line of interest, this is the neutral axis, then you can calculate this two different ways. You get the same thing. So there's the neutral axis. Here's the line of interest in both cases. You can calculate this area A, this centroid, and this distance D. Or you can calculate this area, this centroid, and this distance D. Isn't that cool? Somebody prove that. You have to use integrals and stuff, though, to do it. Prove it for a rectangle, though. You can all do that. All right, so now we know how to calculate everything we need to figure out the stress. So let's do problem. So let's say we have a cantilever beam. And let's say it has a length of 2 meters. And we're interested in what's happening right at the midpoint. And let's say that the cross section of this beam is rectangular. If this is the neutral axis, let's say that, so the whole thing has a height of 0.1 meters. And we're interested in this line halfway between the neutral axis and the top. So this is 0.025 meters, and this is the line of interest. And the thing that's causing this stress is just going to be the weight. We'll say the mass is 100 kilograms. Yes, we do need that. 0.02. Okay, let's think about what we have in this problem for a second. We know how to do stresses due to 3 kinds of loads: tension, compression, bending moment, and shear force. Of those, what kind are we going to have here? We're going to have bending moment and shear force. The bending moment, okay, so what if our line of interest was the neutral axis? Which of those two loads that we have, bending moment or shear force, would contribute to the stress at the neutral axis? Shear force, but not bending moment. And actually, the shear force is biggest at the neutral axis. I should have said that. I'll say that in your notes. So it's always the shear force is going to be biggest at the neutral axis. What if the line of interest was the top or the bottom? What would contribute to the stress at those lines? Bending moment would be at its two extreme values, but the shear force would be 0 because you'd have no area above that line or below that line. Okay. So in order to have both of those two things, we have to be somewhere in between the neutral axis and the extreme edge. Okay, so we don't have to calculate the external loads to do this internal load problem. I'm going to do a cut. Just, we know the line that we're interested in, so I'm going to do it right at x equals 1 meter. Then we don't have to get anything in terms of x or anything. So this length is 1. That's half of the length of this. So it's going to be half the weight. The full weight is 981 newtons. So half of the weight is 490.5, and it's going to happen right at the midpoint. And then we have the tension, shear force, and bending moment. So Newton's second law says 0, negative 490.5, plus T, negative V, is equal to 0. And so T is 0. We saw that that was going to be the case. And V is negative 490.5. And then the moment equation. So first we have a force of 490.5. What's its moment arm? 0.5. And is it a clockwise or counterclockwise moment? Clockwise, so this is all negative. And then plus M minus V times, what's its moment arm? It's X, but X is equal to 1 in this case. So this is equal to 0. So we have M is equal to 245.25 plus V. So that's minus 490.5. And so the bending moment is negative 245.25. This is newtons, this is Newton meters. If you take the derivative of negative 245.25, you don't get negative 490.5. Is that a problem? No. Why? So what's going on here why isn't that a problem? It's not a function, exactly. You can't, so in order for dm dx to be equal to v, you have to know what these are as functions of x. This is just a single snapshot at a single instance, so you can't take derivatives. Basically, we'd just be checking like if this was a constant m function, but we don't know that that's the case, and it's not. All right, so the total stress tensor is going to be the stress tensor due to tension plus the stress tensor due to bending moment plus the one due to shear force plus the one due to torque. Those two are 0, and so we only have to worry about bending moment and shear force. Okay, so for bending moment, we know sigma xx is equal to negative m y over I. We have to calculate that I. It's a rectangle. The rule for rectangles is I is equal to 1/12 times the base times the height to the third, and that is, what's 2 times 10 to the minus, oh man, minus times 10 to the minus 6. Okay, and that's meters to the fourth. The y that we're interested in is y equals 0 is at the neutral axis, so y is positive 0.025. And so the stress is negative of negative 245.25 times 0.025, yep, divided by 1.6 repeating times 10 to the minus 6. And what do you get for that? Okay, times 10 to the 6 pascals. And so the stress tensor due to the bending moment is 3.68 times 10 to the 6. Zeros everywhere else. This is pascals. And now the stress due to the shear force. It's going to be the XY shear stress, and it's equal to negative VQ over IB. We already have I. So for this cross section, this is our area. This is our centroid. The distance we want is this. So area is equal to 0.02 times 0.025. So that is 5 times 10 to the minus 4. And that distance, remember, you're going to the centroid of that area, not just to the line that you are interested in. So the distance is point, you can think of it as 0.025 plus halfway to the top, 0.0125. So 0.0375 meters. And so Q is 5 times 10 to the minus 4 times 0.0375. And what do you get for that? To what? Okay. And the units, that's meters cubed. And then B is just the base at the line of interest. This is a rectangle, so that is just 0.02 meters everywhere. Tau xy is equal to negative shear force, so negative of negative 490.5 times Q, 1.875 times 10 to the minus fifth, divided by I, 1.6 repeating times 10 to the minus 6 times B. Cancel out all the tens before you do the division. It'll save you a bunch of round off error. You can think of that as 490.5 times 18.75 divided by 1.6 repeating times 0.02. And what do you get for that? 2.76 times 10 to the fifth pascals. And so the stress tensor due to the shear force is 0, 2.76 times 10 to the fifth, 0, 2.76 times 10 to the fifth, zeros everywhere else. And so the total stress tensor is, just add those two together, well, there you added element by element. So this is just going to be 3.68 times 10 to the 6 for x, and then 2.76 times 10 to the fifth. And if this beam was made out of a fairly brittle material, and you knew that it, because it's brittle, it's most likely going to fail in shear stress, you would want to calculate the maximum shear stress produced by this loading at whatever point you're interested in. So how would you calculate that? Yep. Now calculate principal stress tensor and then the maximum shear stress is equal to sigma 3 minus sigma 1 over 2. And you compare whatever value you get here with whatever the value is for the brittle material that you're considering to see whether you're worried about it breaking or not. Yes? To find like where it would fail for that material? No, it's not. It's not dependent on the stiffness matrix. It's dependent on other stuff. So you could have two materials with the same stiffness matrix, but one can you can deform permanently forever. You know, like a steel bar, you could, I don't know how much, but you can bend it down to bend this bar, not with your hands like I'm I'm bragging, but it can be bent to a very noticeable angle and still be perfectly strong, you know. Um, if you found some kind of ceramic material that happened to have the same stiffness as steel, before you even saw it bend, it would break, you know. And so that's just a property of like the, you know, the microstructure of the material. That's something you'd have to look up that people would have done lab tests to figure out. And by the way, so when I say a brittle material, well, you would never really make a beam out of a brittle material, I'm guessing. But maybe you would for some reason. Um, but so if you had this ceramic thing, that what brittle means is that you can't deform it permanently very much before it breaks. Uh, Once it leaves that linear elastic range, you're basically done being able to deform it before it snaps in two. Whereas metals, and some metals more than others, this wouldn't be a very useful criterion for figuring out when it's going to break, because, you know, metal, you could bend this beam over at 90 degrees and it would still hold. So then you have to use sort of more complicated calculations to see whether you're worried about it breaking. Although this would still be useful for determining whether you're concerned that this steel bar is going to deform permanently if you're trying to avoid that. Max? Yep. You just plug that into your eigenvalue calculation. It gives you your three principal stresses. For triangle rule. Oh, for this? Um, yeah, right. I don't know what it is, but there is. But you know, how much easier could it be than plugging that into your calculator and calling the eigenvalue function? Any other questions? Okay, that's all. Good luck tomorrow, everybody. That sucks, man.